So this is a, revision of the chapter called as a baseband data transmission, wherein the first concept was the features of what is called as a baseband data, right? So baseband, in the sense, it is the most original format of the data, uh, right? And it is normally in the analog format, right? So when we convert the analog format into the digital format for the purpose of transmission, as well as for the purpose of processing, and maybe the saving the data in the inside the computers, we know that we need to convert that into the digital. Okay, so digital means you have to perform the sampling along the x-axis as well as the y-axis. So when you sample along the x-axis, that is called as a normal sampling. The word sampling refers to performing the quantization along the x-axis. You define that, okay, I'm going to do the get the samples at a specific time, TB2, TB3, TB dot dot dot. Very similar to that. On the y-axis also, you can perform what is called as the sampling, but it is called as a quantization, right? Different predefined levels are going to be used for that purpose. Okay, that's one way. Like I try to gather the data in the discretized form, right? And coming to the different views of data, right? You can get the Fourier representation of the data so that you can look at the details of the function or the signal in the frequency domain, right? Another version, right, of looking at the data in terms of the power is called as a PSP, power spectral density. What is the use? You will come to know if I want to have a communication of the specific requirement, right? Use you are going to supply at least this much of the power, right? What is the amount of power you need to put at various frequencies? You will come to. Okay, so that's why the PST representation becomes very important. All right, now, so the first topic, actual topic begins from here, which is called as a discrete PAM representation, which is the pulse amplitude modulation. Right? We try to modulate the amplitude of the pulse depending upon the message data. So normally, you see, we are trying to send the data in the binary format, right? Whenever we say it is in the binary format, we know that there will be only two levels, one level for 0 and another level for 1. Okay, so those are the two levels. Now in PAM, what we do, we use various types of pulses, right, or various shapes of pulses for sending either 0 or 1. So there are very standard pulses given, right? Again, we saw by considering a specific bit sequence, right? And we also try to understand how do you use various PAM techniques to convert them into the required format. Okay, so this is the data set 1001101. So that was the data set. So first technique we used was NRZ unipolar. So as the name suggests, unipolar refers to single polarity, right? There is one polarity and the polarity is assigned for uh, bit 1, and for 0 there is no polarity. The amplitude or the magnitude will be 0, right? So that's what is the representation. You can see here, right? Wherever we are using, we are sending the 0, we send, right, like this. So wherever you send 0, there is nothing, it's empty. Okay, but wherever we have wherever we have 1, right? So the ones are sent according to the amplitude. So okay, 1 means it is 1. In the sense, you can even change this amplitude to plus a and 0, right? So just see what exactly has been followed in your syllabus, in your institute, so that you can follow the same thing. All right. So the second technique is called as return to 0 unipolar. In the same unipolar format where polarity is either 0 or 1 or 0 or plus a, the signal is going to come back to 0 after, right, some time, right? In the sense, whenever it is 0, it's already 0, so there is no question of coming back to 0. But definitely, yes, whenever the amplitude is 1, it can come back to 0, right? When it comes to 0, let us assume that the total distance or the total sampling duration is, right, TB. Half the time it will retain the plus 1, right? The polarity related to 1, that is plus 1, and remaining duration it will be, right, 0. Okay, so that's what is the idea here. You can see here, right, in this case you can understand that, right? This is what is happening. It is one for, sorry, it's one for certain duration, and then it comes back to 0. Okay, right? So that's notation for this. I'll just yeah, this is what. Right, so that's the second one, RZ unipolar. Then we have RZ polar, right? It is written to 0 but polar, right? When we say polar, there will be two different poles, polarities. So one for representing one value for 0, one for 1. So normally 1 will be represented by a positive quantity, that is plus 1, right, or plus a, and 0 will be represented by another polarity, that is minus a or minus 1. So you can see, since it is written to 0, right, every polarity will be retained only for half the duration of the or half the bit duration, right? Remaining half it has to come back and maintain the 0 level, right? So that's what is RZ polar form, written to 0 polar. The next format is non-written to 0 polar. So polar means there will be two polarities by default, right? Again, it is not coming to 0 throughout your bit duration. That particular level will be maintained. So NRZ polar, you can see 1 is completely 1 bit duration. For 0, it is minus 1 for the complete bit duration. There is no returning to 0. So in this case, you will never see the level 0 in the whole graph, or right? Throughout your signaling period, you do never see a 0, right? So that is NRZ pole. Okay, similar to that, we have another technique, that is NRZ bipolar. So the word bipolar refers to for a single, what you call, single, say bit, say 1, right? Only for 1, there will be two polarities. Bipolar means there will be, right? Totally how many levels will be there? Totally 3 levels will be, right? 0 will be completely 0 always. But if I have consecutive ones, the first one will be plus 1, then the next one will be minus 1. If you followed by that, if you have one more one, the third one will be once again plus 1. So alternative plus and minus signs for consecutive ones only. No problem with 0. So for zeros, it will not change. All right, so that is NRZ bipolar. You can see the same thing happening over here, right? Whenever the symbol was like this, right, we had two consecutive ones, and for two consecutive ones, we never had, right, same levels. The two different levels are being used. Okay, then we have RZ bipolar. So it's a bipolar technique, but you have written to 0 concept, right? Whenever you have two ones, right, there will be change in the sign, that is plus a to minus a or plus 1 to minus 1. In addition to that, every value will be retained only half the duration. Okay, right. So that is RZ bipolar. Then there is another technique that is represented as a Manchester, or it is biphase. Right. There are two phases, right? One will have one phase, 0 will be having the other phase. So phase could be defined in this sense. So you see, when we try to represent one is actually, right, half the bit duration it is 1, remaining duration it is minus 1. So that you consider as one phase. Okay, at the same time, you can see here zeros are represented in the reverse phase, like initial half bit duration it is negative minus 1, then it will be plus 1. So phases are actually reverse for 1 and 0 here. So if you try to represent this kind of notation throughout for your signaling period, the waveform you get is considered as a Manchester form, right? So normally one normal question is that they give a specific bit sequence, right? And they will ask you to plot maybe one or two of this. That's what is expected in normal case. Yeah, Manchester. I'll explain once again. So Manchester, you see, the for bit 1, right? What we are doing here for bit 1, it's it's high for first half and low for the second half. But 0, you see, it's a reverse. Low for first half, high for the second half. That's all. It's repeated. So next to 0, low, then high. 1 means first high, then low, high, low, and so on. It's just that. So just remember what is 1 and what is 0. Okay, so remember that and you keep right following the same thing throughout. Right, whatever is the given data sequence, you can follow that. Okay, so that's how that's what will be the representation of Manchester. Right? Do you have any doubt with any of these plottings? All right. Okay. Now we'll proceed. We are going to consider the power spectral densities of various types of waveforms we considered so. Okay, first one. Uh, let's look at uh, what do you mean by PSD and how to calculate. So now we have, and let's assume that I have any of these formats, and it is represented in x of t. So x of t is equal to, right? I have some amplitude represented by ak, right? This is the ak value in equation 1, and I have v of t minus kt. So v represents the pulse shaping function, whichever function you are taking, nrz polar, nrz bipolar, or whatever out of those, right? That is represented by v of t. 0 will be represented in some sense, the 1 will be the other way. Okay, according to that. Right, now you see at different locations, right? You can see this, I'm referring to the diagram written here, right? V of t is at the center, but V of t minus ktv will be shifted versions. Depending upon the k value, you can see 1 TB, 2 TB, 3 TB at the x-axis. That's a time axis. So we know, we have studied from in signals and systems that if the k value is positive, like 1, 2, 3, signal gets shifted to the positive side. That's the right side of the y-axis or right side of its current position, right? So that is a right shift. So in which the function still remains as v of t minus kt. Okay. If at all you have k value being negative, so you see v of t minus of minus k, right? It becomes plus k. So v of t plus ktb will be the left shifted versions of the same function. All right. So we can cover the complete x-axis if you use a k value from minus infinity to plus infinity. So that's the reason why you see in equation 1 we have k varying from minus infinity to plus infinity. Okay, so k is minus infinity to plus infinity. That actually takes care of the complete movement of your v, that is a pulse shaping function, all the way from minus infinity to plus infinity, indicating that wherever it is needed, right? You may not shift all the way from minus infinity to plus infinity, but wherever it is required. Okay, so that's what is the k, the variation in k refers to. Right, you see amplitude multiplied by this pulse shaping function or shifted pulse shaping functions gives you the complete representation of the binary sequence, right? So binary sequence you considered earlier was 0, 0 something, right? 1, 0, 0, 1. But you see, we represented that using different formats and the waveforms will look like this. Right, so different waveforms we have, and each of the waveform is the corresponding representation of some amplitude. Normally, in this case, you see what we are seeing in the graph. In these graph, we considered for simplicity highest amplitude, or the 1 is considered as 1 volt and 0 is a 0. Okay, or negative 1 is minus 1. But practically, you see, right, there will be some values associated with that, because 0 means it will not be a 0 volts or some minimum volt like 0.3 volts in practical values. Okay, similarly, plus 1 will be the value corresponding to high, like 3.3 volts or 5 volts or something like that. Okay, always the representation is in the same fashion. Okay, now we know that the x of t is any one of this waveform. Okay, right? So after x of t, now what I'm trying to do, I'm trying to represent its Fourier representation, because I want to go to the frequency domain. Yeah, small x of t, right? So Small x of t is a time domain waveform. Any of the previous waveforms we saw, right? That is x of t, right? You see, it is actually called as a line code because of the same reason, right? I can see different levels represented by different lines. So line code, right? So in that v of t, anyway, we understood that is a pulse shaping function. Capital TB is the duration of the pulse. One duration, right? How much time you hold the plus one value? How much? What is the duration of the minus one? What is the duration of a zero? Right? One bit is represented by that. We call it as a pulse duration. Okay. And also we have AK, that is a polarity used, right? It varies, right, depending on the system, right? You can have plus one, minus one. That's for simplicity. Definitely you can use plus a, minus a, and zero. All right. Okay. Let's move further. Now, how do you write the equation of a PSD? If I have an equation of my waveform in the form of x of t, right, then it's what you call the PSD is denoted by Sx of f. Okay, PSD notation is capital S. That's the standard one, right? And small x denotes it's my waveform. That is the waveform which I'm considering time domain denoted by small x. And inside the bracket I'm writing f because I'm jumping into the frequency domain by taking the Fourier representation, right? So that's the meaning of this notation. So this is a very standard equation. Okay, so for taking any signals PSD, you need to have 1 by TB magnitude of V of f the whole square into summation all the way from minus infinity to infinity. There is a parameter coming that is called as Ra of n, and it will be e to the power minus j2 pi f into n into capital T. Okay, so the result comes in f domain because you have a summation of the variable is n varies, tb is a constant which is a variable here, that is f. So f is a variable in equation 2, right? There is one, tb is a constant. See, magnitude of v of f square. So v of f is still there. Yeah, v is capital. That is, I'll tell you what capital V is. So already we had a small v here, right? That is a v of t, pulse shaping function. I'm taking the Fourier transform of that. That is denoted by capital V. So again, you can understand that there is a Fourier transform being taken, right? By just looking at this, because inside the bracket I have f here. But you see, look at the next line. V of f is the Fourier transform of V of t. Okay, so but we have not seen what is RA of n. It is called as a autocorrelation function of the given data. And there is a fixed formula to calculate that every time. So summation sum I is my variable going till capital R, where capital I will be the number of combinations you can get for AK into AK minus n. So inside the bracket, equation number 3, you can see that there is a AK into AK minus 1, right? How many ways you can generate that, right? That is the number capital. Small I will take all the way from 1, 2, 3, 4, dot, 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 up to capital I. That's what is the meaning of this notation, right? Into Pi, that is the probability of occurrence of that product. Is it okay? So in how many ways you can get this done? So that is what is the representation. Okay, right? So all the parameters we define now. So ultimately, if you want to calculate the power spectral density, I just have to use equation number 2 and substitute the various parameters such as V of f and RE of n over there. Okay, once you put that, it means yes. Once you put those values and simplify, you get the required answer. Is it okay? All right. Now, very standard waveforms only we will consider. The first waveform is NRZ unipolar, widely used in the communication. That's why this is the first one. So you see, how do you represent that? I have two levels. AK is equal to plus A for symbol 1 and it is a 0 for symbol 0. Right? I also need the probabilities to substitute. Right? We assume equiprobable case. Right? Whenever AK is 1 and AK is 0, both occur with equal probabilities, right? That is equal to half. Okay, so always you remember whenever we solve this equation number 2, first we calculate RA of n required and then we'll calculate V of f required. Then you substitute both in the equation 2. Okay, so now what we are trying to do for case 1, which is NRZ unipolar format, I'm first calculating the value of the RA of n. Is it okay? So first you try to calculate that always. Right. We are trying to do the same thing now. So as of now, I'm trying to calculate that area of n. So first, in the area of n, inside that I can see that, right, there is a p required, probability, right? So that probability also we need to write. So what is the probability that it takes a value 1? That is equal to, probability that it takes 1 is equal to how much? Half, right? Again, it taking the value equal to 0 is also half. Okay, so anyway, we got those values. Let's try to calculate the various values for RA of n. Normally, you start with 0, right? So put n equal to 0. That means the inside the equation, inside the bracket of that summation, you need to put n equal to 0. So normally you can see that this is ak into ak minus n, right? Now n is equal to 0. That's ak into ak. So you can see n equal to 0, right? I need to find out how many possible combinations. So there are two cases. Like when I consider ak as 0, it is 0 into 0. That's first combination. And whenever you say ak into ak as 1 into 1, that's the second combination. I cannot have any other combination because I have only two values, right? So I is equal to 1 to 2, right? ak into the individual probabilities. So we'll expand this. So a into half. Once again, 0 into 0 into half. A into a, because it is 1 into 1, right? 1 is represented as a. Okay, so simplify, you get a square by 2 as the answer. Okay, right. Next, you make sure that the next possibility, definitely I can put n equal to 1, right? When n equal to 1, you are trying to consider non-neighboring sequences, non-neighboring data points, right? Like I can have 1 followed by dash, doesn't matter. After that, whatever it comes, you can have a 1 or 0. Like whenever right now I have 1, the samples next to next will be 0 or 1. So I have that combination. Similarly, if you have a 0 now, right, the next to next data point can be once again 0 or 1. So I have four combinations: 0, 0, 0, 1, 1, 0, 1, 1. That's why we club all the other possibilities like n equal to 1, 2, 3, 4. Everything will be classified into one category, that is equal to n not equal to 0. Are you okay with that representation? Why we called it as a single this thing, right? Yeah. So because of that, now we got this value, and let us try to substitute all the possible values over here, right? So you can have 0, 0 as we know, right? Earlier we have seen that. And also I can have 0, 1. 1 is a, so 0 into a, and 0 into a into 0. And also I can have the next value coming as a into e, out of which, again, you see the probabilities, that's 1 by 4, because there are four combinations, I have one. Okay, right. So only the last one gives you the answer, that is equal to a squared by 4. Right? So the conclusion is that whenever n is not equal to 0, right, we are going to get the autocorrelation value as a square by 4. So club both the answers you got so far, one for n equal to 0 and one more for n not equal to 0. Right? Both of them will club together to get this equation number 4, which is right like this. RA of n is equal to a square by 2 when n equal to 0, and a square by 4 when n is not equal to 0. Correct? Okay. Next is, let us try to look at the unipolar form. Right? You have one polarity for 1, and right, you have the other polarity like 0 for 0. But try to represent the equation format of your pulse. So from signals and systems, we are taking this concept, right? If in signals and systems, we know that if you have the pulse like this, which is shown in the graph here, we expect that in order to write an equation, we expect that to be right uh, symmetric about y-axis. Like on one side I have TB by 2, other side is minus TB by 2, amplitude remains same. So for that, this is the equation, rect of capital small t by the duration, which is capital TB. So capital TB is the total duration of your uh, pulse. So how do you write? If you want to expand that and write, you will write it is equal to 1 for magnitude of t is less than TB by 2. That is minus TB by 2 plus TB by 2. Otherwise, this is equal to 0. Okay, this is one of the very standard function. Okay, it's one of the very standard function, and because of that, we know its Fourier representation. Also, we are taking this directly from the signals and system. So if you have a function v of t equal to rect of t by tv, its Fourier transform will be right denoted by v of f equal to capital TB into sinc function of f into tb. So now you see we know RA of n, we also know the v of f. So once you know both of them, substitute in the equation corresponding to the calculation of Sx of f, which I have written in the first line over here. So, right, what I do, I understand that the RA of n has two values. One for it is equal to 0. So, RA of 0 I'll write outside. And the second value where the summation still remains all the way from minus infinity to infinity, but that does not contain n equal to 0, right? So, n not equal to 0 we'll write, then we write as is. So, RA of 0 will be a square by 2. So, in the next line you can see I'll write that. Okay. And also I'll substitute for v of f, which is TB square, sinc square of FTB. Okay, so out of which TB and one of the TB in the numerator will cancel, right? And inside the summation, right, we can see that there is a term which says that n is not equal to 0, right? But when n is not equal to 0, if you have a discontinuity in the summation, there is no substitution for that. So that's what is a mathematical issue we are facing here. So what I do, I try to substitute the value corresponding to n equal to 0. So in this term, in the previous line, whatever you have, put n equal to 0. That is e to the power 0. Correct? What is e to the 0? E to the 0 is 1. Correct? In the sense, if I add the point corresponding to n equal to 0 and subtract the point n equal to 0, then there is no change in the summation. Correct? So what I do, you see n equal to 0 means it is plus 1. I added the plus 1 here and I subtracted the same thing by doing a minus 1. So actually, strictly speaking, no change in my function. Right? But what I do, I add the plus 1 to the summation. Next line you can see here, right? I am making the summation n equal to minus infinity to n equal to plus infinity. Can you see here? So 0, which was in the previous line, I wrote n not equal to 0. Now I eliminated that because I included the n equal to 0 into this. Right? How did you compensate? There is a minus 1 outside. Okay. So anyway, a square by 4 was a constant, so we could keep it outside the summation. Anyway, the variable of summation is n. So as far as you don't have a n over there, you can keep it outside. All right. Okay. Now let us try to expand this, multiply this, right? So you can see that. All right. So you can see that there is a square TB multiply. So we have a square TB into sinc function, multiply the first function, you get that. And then you can see that you have the second function, that is this, right? Multiply it, and the summation is also there. Okay. And last term will be multiplication with the 1. Okay. So when you do that, you get something like this. Is it okay? Okay. Look at the next term. We have a standard function coming up. So the standard function is what is a standard function? We have a substitution for n in equal to minus infinity to plus infinity. the exponential, right? That exponential can be replaced by, right, 1 by TB into, you can take another variable over there because anyway, n is already used on one side, right? So I don't want to use that. Okay, so because of that reason, we have substituted just like this 1 by TB into, it's a delta function. So sum of the exponentials, the meaning is like this. Sum of all the complex exponential, all with the integer multiples of what you call integer multiples of the frequencies, right, is nothing but you can replace that as a delta function. Again, delta functions replaced at integer multiples of 1 by t. M is your variable, delta function, f minus, it's a shift, right? You can see again the function is getting shifted all the way from minus infinity to plus infinity. So that means you have a delta function, delta of f, right? Shift it to right by making it as 1 by TB, 2 by TB, and so on. Shift it to left by making it as minus 1 by TB, minus 2 by TB, scaled by a factor 1 by capital T. Okay, so that's what is equation number 7. Now we can see that the same thing is happening here, right? We try to represent that here to understand that. So what happens now? The whole equation becomes whatever you see here as equation number 8. Okay, so a square capital TB by 4 sin square of FTB. Then I have a product coming into picture because of the substitution, right? Right, whatever there was a summation, I replace it as 1 by TB into summation m is minus infinity to plus infinity delta function, right? You see there is a product, right? One is a sinc square function, another function is the delta function, series of delta function, the Coombe function, correct? So in order to understand what is this, how do you get the product, right? We will consider the following diagram. So the sinc square function, you can see the first diagram. Okay, first it's a sinc function, right? Starts from 1, it becomes 0 at every 1 by TB, 2 by TB, 3 by TB, and so on. Every integer multiple of TB, it is 0, right? Whereas the second delta function is, right, the delta values located at m by TB. So m by TB is 1 by TB, 2 by TB, minus 1 by TB, minus 2 by TB, and so on. Everywhere you have this. Now, if you take a product, right, I get only one sample, that is delta of it. Correct? So you see, this is the Sx of f, which is the power spectral density. So a square capital TB by 4 sinc square of FTB. That's the original first term which we have since beginning, right? Only right now, after simplification of that product, we got delta f and we replaced it after a square by 4. So delta function gets scaled by a square by 4. You can see here, this is the waveform. And the sinc square function gets scaled down by a factor a square into capital TB by 4. Okay, normally this TB is very small, so a square by 4 is bigger, a square TB by 4 is smaller. That's why this amplitude is smaller than a square TB by 4. Okay, is it fine? Do you have any doubts with this? All right. In that case, we'll go to the second format and we'll try to represent in equation format of its PSD, and we'll try to plot this. And right now we are going to consider the non-return to zero polar form. Okay, so if you remember the polar format, I will have two different polarities, one for +1, one for symbol 1, one for 0. So for this particular analysis, we are considering symbol 1 represented by plus A, symbol 0 represented by minus A. Okay. Also, our first intention is to calculate RA of n, the autocorrelation. So calculate the probabilities. Normally, you keep it equiprobable. That's why both are assumed to be half and half. Is it fine? Okay. Now, so we use the same equation for RA of n. So summation small I to capital I, ak minus 1 I times multiplied by individual probabilities. So start with n equal to 0. It means ak into ak, right? So ak into ak means, right, there are two chances, one with aa, other one is minus a minus u, right? So both, there are only two chances, right? So when you have two chances, they are equiprobable, so 1 by 2, 1 by 2. Okay, right. So we have a square by 2, and the second term is also give you the a square by 2 itself. So totally it becomes simply a square, right? Then proceeding further, let's look at Ra of n for any value of n other than 0. So once again here we have four cases because the next to next term will be like current term is a, the next to next term will be a or minus a. So I got two chances over there. Two more chances, like I have the current bit as minus a, next to next bit will be plus a or minus a. So two more, so totally four, right? So now you see when n is not equal to 0, the area of n will be represented I is equal to 1 to 4, right? Ak into ak minus n I pi. So substitute all the possible value, you get a into a by 4, a into minus a by 4, minus a into a by 4, minus a by 4, out of which plus a, right? And so sorry, all the terms will get cancelled here, right? So a square by 4 minus a square by 4, same thing repeated, so everything cancels. So when n equal to 0, you have a value equal to a square, and when n is not equal to 0, you get that value equal to 0. So to summarize, you can write an equation as shown here. All right, so area of n is equal to a square when n equal to 0, it is 0 when n is not equal to 0. Right. So what do we want? We can now we have the values ready with us because the v of t is still same. It is rect of t by t, irrespective of whether you have right positive a or minus a for the representation. The rect function still remains same, right? It's a rect function multiplied by plus a gives you the positive waveform, which you can see here. If the same rect of t by t be multiplied by minus a, I get the value below the x-axis. So irrespective of what you have, whether you have plus a minus a, my v of t remains same, right? So whenever I say that the v of t remains same, you can understand that I can still use the same v of t we used earlier, and we can write the v of f like this. Okay, v of f is still remains same, that is capital TB sinc of ftb, right? Now only RA of n changes, others will remain same. Okay, so Sx of f equal to 1 by TB magnitude of v of f whole square summation Ra of n e to the power minus j 2 pi f n TB. Is it okay? Huh. Y-axis is simply amplitude in these waveforms, right? A and minus A, right? You can you can simply mark it and call it as V of t. Okay, that's right. So fine. Now you substitute. So 1 by TB, V of f whole square will be TB square sinc square function into, now you see minus infinity to infinity has no meaning because only one value exists, that is for 0. So simply remove that and write RE of 0. And when n is 0, there is no e to the power function because e to the power 0 is 1. Okay, so you got it. This is very simple. Substitute a square and write it as a square TB into sinc square of f TB, right? And on the right hand side, you can see the graph corresponding to that. Okay, so it is a square TB, right, is a magnitude. Sinc square function will be 0 at 1, 2, 3 because your x-axis is now ftb. Okay, it is not TB. If at all it's not f. If you write f, the values will be 1 by TB, 2 by TB, and so on. As you want, whatever is convenient to you, you write. Okay, if you write f as an axis, the values over here will be 1 by TB, 2 by TB. That's the difference. All right. Okay, second format is over. Next format is the uh, NRZ bipolar format. So as you know, the bipolar format is going to have two polarities for consecutive ones only, right? There will be changing polarities for one, and symbol 0 will be the same polarity. So now you see, say the probabilities are going to change. So totally chance probability of getting a 1 is half, getting a getting a 0 is also half, right? But A has internally A gets divided into two, right? Two parts. So the A will be divided the probability of A gets divided once again. So that is P of plus A is 1 by 4. That is 1/2 of the half. 1 by 4. P of minus A is also 1 by 4. Okay, that's the change we need to do in this case. Anyway, so we defined AK plus or minus A for symbol 1, 0 for symbol 0. Now directly go to the calculation of RA of n. So first we'll do n equal to 0, right? So what are the chances you have? Only 3 chances now, because you can have 0, 0, A minus A minus A among this, right? So you substitute their values, right? A into 1 by 4 minus A 1 by 4, you get A squared by 2. That is when n is equal to 0. Okay, then put n equal to 1. Now again, in this case, there is a difference. Okay, when n equal to 1, we need to look at that the as a special case. Now you see, when n equal to 1, it means I am supposed to look at the current value and the next value. So whenever you are looking at the current value and the next value, just think what's happening. You may have 0 and 0. Fine. You may have 0 and 1 represented as 0A. Okay. But next one could be, I can have a plus A and 0 or minus A and 0, one of them. Right? But if you have a plus A, the next one will be minus A. And if you have a minus A, the next one will be plus A. Right? These are the various combination. Again, I wrote a combination inside this, right? On the right hand side, you can see these are the 4 possible combinations. Right? None of the other combinations exists over here for this n equal to 1 case. So each one of them, there are 4 chances, so 1 by 4. So multiply and get the answers. First 2 terms will cancel. 3 terms will get cancelled. Only the 4th term will give you minus of A square by 4. The minus comes into picture because first one is A minus next one will be minus A. Okay. So first one is minus, next one is plus. So either of them you consider, I have a minus coming out. All right. So that is minus of A square divided by 4. All right. Then now you consider any value greater than 1. That means current value next to next value or next to next value, third value, fourth value, and so on. So now that doesn't make any difference. All of them are considered under the same case, right? So what are the chances you have? You consider. So 0, 0 is a case. 0A will be a case. 0 minus A will be a case. I can have a current value 1, middle 0, then the next one will be once again, right? It can be something like A, like A. If you have a minus A right now, next one will be A. Okay, but A minus A is not possible, right? So we have 5 different possibilities and we try to substitute their values like this. Okay, and you can see that again everything will be going to give you a 0, right? Terms will cancel and you get a 0. So any value greater than 1, the autocorrelation function generates a 0. Is it fine? Okay. So summary of the autocorrelation function is like this. RA of n is equal to A square by 2 for n is 0, minus A square by 4 for n equal to 1. It's 0 for n greater than 1. Okay, right. But only in this case we need to apply the symmetric property of ACF. That is, whenever you have a sample valid for RA of n, it is also valid for RA of minus n, right? That means it's a symmetric. You shift to right by 1 unit, you shift to left by 1 unit, it remains same. That's what is a overall big picture, right? So let us try to update my RA of n like this. So A square by 2 for n is 0. So far we got only for n equal to 0. That's why we never observed this. Okay. But now since at 1 you got a value, at minus 1 also it should retain the value. Correct? So you see now we update it, right? The value will remain as minus A square by 4 for n equal to plus or minus 1. Okay? And it is 0 for n greater than 1. Okay. Right. So that's the area of n. Again, the rect function remains same, rect of t by tb. Take a Fourier representation, you get v of f. Capital TB, sinc of f, ftb. So use the same equation for Sx of f, where I need to substitute v of f as tb square, v of f whole square as tb square, sin square ftb. Then only the summation has three values. N is -1, n is 0, n is +1. Other values, it's going to be 0. So there is no need to write the summation as it is. Simply expand. Right? Whatever you see here is the expansion of the summation by making zeros for all the other values other than n equal to -1, 0, and +1. Is it okay? Right. Next. So substitute, simplify and substitute the values of RA of -1 as -a square by 4, then RA of 0 as a square by 2, and RA of 1 as -a square by 4. Okay, now I can see that there is a e to the j theta and e to the minus j theta added. With the common factor minus a square by 4, I take that out in the next step. Right? So anyway, outside I have capital TB, sinc square of FTB. Inside the bracket, I took minus a square by 4 common. I retain the e to the powers inside the bracket. And there is a term, separate term, a square by 2, which is outside. So we know that e to the j theta plus e to the minus j theta is nothing but a cos function. It's a right. Normally, it's e to the j theta plus e to the minus j theta by 2 will be a cosine. But in this case, I don't have a 2 in the denominator. What I can do, right? I can simply make it as a, simply write it as 2 theta, 2 cos theta. So once you do that, you get the a square by 4 into 2 cos theta. 2 gets with the cancels with the 4, right? Denominator gets a 2, right? I also have plus a square by 2, right? The a square by 2, I'll try to take it out as a square capital TV by 2 sinc square of the function. Inside the bracket, I have 1 minus cos of 2 pi f into t. Right, again substitution. Yeah, the whole theta can be considered as a 2 pi ftb, whatever you have, right, inside that bracket. So now I have 1 minus cos 2 theta. So what is 1 minus cos theta? 2 sine square theta. Correct? So replace. So I have a square tb by 2 sinc square ftb as it is. Then 1 minus that whole function inside the bracket can be 2 sine square of the half angle, right? So 2 pi ftb becomes simply pi ftb. Right, so that's just because whatever is inside the bracket you consider that, right? It is, you consider that as 2 theta. So right, so 2 theta becomes just theta, right? So that's why this is how it's going to look like. The simplified answer I wrote here, that is Sx of f equal to a square capital TB sinc square of ftb multiplied by sine square of pi ft. So this is how it's going to look like. I have a sine square function. You can see this is just an approximation, right? I wrote a sine square as a second graph on the right side. So I have a sinc square function once again written in this way, right? So you see, initially first function has a 0, second function starts from 1. So 1 into 0, it should start from 0. So you can see Sx of f, right, in this fashion. It starts from 0. So it goes to a medium height around halfway through, then comes down, because at 1 both the functions are 0, right? It has to go to a high value, then comes to 0, then once again high, then comes to 0, and so on, right? At ftb equal to 1, 2, 3, 4, it's going to have 0. But only difference of this waveform, this power spectral density compared to all the previous ones is that, right, this is only halfway through. Okay, initially it starts from 0. All the other PSDs were starting from 1. Right. So this requires it. It's like the meaning is that it has no DC component. First thing to understand, and at the low frequencies you have low power, right? So around close to 0, you don't have any power required, correct? So and only in the halfway through between 0 and 1 you have some power requirement. So this method, it has a DC component, because starting at 1 means what is the f value? F is 0, right? F0 means what? DC. Yeah, that requires, Yes, you see, that means it has much more power than that, than the normal one, right? So highest power required by the first waveform. Then moderate power. Power is slightly lesser than the first one. That is the second case. And this third case is least power. All right. So if it starts from one, it has some DC component. If you have another function over there, it requires much more power than that, because there is a delta function plus the power, DC power required over there, plus whatever else. Is it okay? So many, there are so many, what you call, aspects in the PSD to understand that how much is the power required. The next topic is called as ISI, which is inter-symbol interference. So as we know, right, during the communication process, the symbol which is sent at one position, right, has a tendency to spread its energy into its neighboring symbols. Yeah, so that's what is called as a ISI. But before going into the actual concepts of ISI, we will look at the general diagram which actually explains the complete communication process, right? So let us say it starts with the input, that is a binary data. Normally, that binary data will be converted into x of t, that is a pulse, right, using the pulse generator. So followed by that, you have the transmitter. The complete transmitter is represented by a filter-like representation. In the sense, you try to give an equation, right, for the for all the operations that performed by the transmitter. We call it as a transmitting filter. So the notation for that is ht of f. So, right, this whole part is written as Tx over there, indicating that this is a transmitter. Whatever is the output of this transmitter, it is given to the channel, right, which is the medium used to carry the transmitted data in the form of a signal to the receiver, right? So again, the channel, if it is ideal, it keeps whatever is given as input from the transmitter as it is, and it makes that message to reach the receiver without any, right, changes. But the practical case is that it is not like that. It will change the amplitude, it will bring the phase shift into picture, etc., right? It will select certain frequencies, and it will attenuate certain frequencies, etc. Many things are going to happen. So the response of the filter, response of the channel is written as a filter, that is denoted by hc of f. Again, this is in the frequency domain, right? Then you can see there is a receiver, right? The job done by the receiver is denoted by hr of f. So after that, we get a function denoted by y of t. Right. So y of t is a continuous function because t is a continuous variable. But our intention is to get back the symbols, right? Whether it is 0 or 1. So what you do, you try to sample it out. So the sampler is denoted over here, which is sampling your y of t at every value of tb. So you can write it as y of itb. I varies from 1, 2, 3, 4, dot, dot, dot. Okay, so this part is denoted as Rx over there, which is the receiver, the notation for receiver, wherein the final decision is taken by the decision making device, which uses certain amount of threshold, right? With the threshold, you compare your sample value, that is y of ITB, right? Once the y of ITB, maybe if it is greater than threshold, make it 1, lesser than the threshold, decide it as 0. So that decision part we have not written here, but simply we wrote output. That is a binary sequence. Okay, this complete block diagram represents what is called as a baseband binary transmission transceiver system. There is a uh, transmitter and there is a receiver. So because of which we call it as a transceiver system. Okay, so it actually has both the parts. Now, so once again, we'll go back to our original equation saying that we start with the x of t. So x of t is equal to, as you can see here, it is k is equal to, say, minus infinity, 2 plus infinity, ak, the amplitude value, into a pulse g of t minus kt. Right. So normally we try to we start we do this analysis considering that it's a proper rectangular pulse. But in the actual communication, you can use various other types of pulses as well. But for the time being, let us say g of t is a rectangular pulse, and the at the center of the pulse, it is going to have a magnitude of 1. Okay, now we consider the various possibilities of capital AK. So we know that capital AK can take a value plus A for symbol 1, minus A for symbol 0. And capital TB is nothing but the bit duration. Okay, all right. So let us consider the Fourier representation of the G of t. So Fourier representation of G of t is nothing but, let's say we have, again we don't know the exact equation of g of t, so right, we simply call the Fourier representation as g of f. Okay, so when this is g of f, if at all I shift my function g of t to g of t minus t naught according to the basic properties of Fourier representation, you need to multiply that by e to the power minus j 2 pi f into t naught into the original function, that is g of f, on the right side. So this is what is called as a time shifting property of the ft. Time shifting because g of t became g of t minus t naught. What is that? That's a time shift, right? So because of that, what happens on the frequency side, if you calculate, that is called as the time shifting property. Okay, fine. Anyway, we know that the equation. So sorry, we are not writing a sinc function as it is because it can be any other type of rectangular function. The one which we considered earlier was having a proper equation, rect of t by capital TB. Okay, right now, yeah, other versions also. Okay, that's why we are simply writing it as a g of t and g of f as the Fourier pairs. Okay, so we have x of t. Let's take the x of f now. So x of f becomes equal to, there is one very peculiar feature of right, this kind of function, right? If you have a summation, the summation will be retained even on the frequency side. So you can see equation number 3 has once again summation ak into, it was originally g of f, but since it is shifted, you will write g of f into e to the power minus j 2 pi f k t. Right. Now, so what we do, we refer to our block diagram, and the block diagram says there is a receiving signal. After you receive the signal and the signal passes through the receiving filter, we had denoted that as a y of t. Correct? So that y of t, right? We have to make an assumption that, let us say we send a pulse from the transmitter side. Okay, that passes through the transmitting filter, passes through the channel, and passes through the receiving filter and comes out as y of t. Now you see, right, the pulse will be retained even on the output side, but it may not be the same pulse. The pulse may get changed. So we started with the g of t. Look at the equation number 4, right? So what we are writing here, we are writing it as p of t minus kT, where p is a different function. We started with the g of t. G of t passed through all the filters like transmitting filter, channel, and the receiver, comes out of that as a p of t minus tt. That's the first thing. Pulse will be changed. All right, pulse gets changed. Right, right, and also the amplitude which was ak on the transmitter side, we may assume that the channel changes, that channel attenuates that by a factor mu. So mu into ak can be seen in place of simply ak. Is it okay? So mu into ak comes into picture, which makes sense, right? Because there is a attenuation factor. So because of which we have, right, like this. We have written like this. Now you see the explanation goes here. P of t is the pulse shaping function of the y of t, that is the received signal, Again, we assume P of 0 is 1. And let us say there is a scaling factor denoted by mu. So here also we are going to use the shifting property. P of t has a Fourier representation P of f. P of t minus t naught will have the P of f getting multiplied by the exponential e to the power minus j 2 pi f into t naught. Okay, that's the property which we are using. So using that, I can take the Fourier of equation number 4. So equation number 4 has y of t, it becomes y of f equal to summation is retained. Mu ak is a constant, retains. P of t minus ktb has a Fourier representation, P of f into e to the power minus j 2 pi f kt. Equation number 5. Is it okay? So we'll hold on to equation 5. We'll substitute, we'll come back to this later. So we'll go back to the diagram, block diagram, and we'll try to understand if I have x of t in the time domain, x of t's Fourier will be x of f, capital X of f. So that in the frequency domain, you need to multiply. So in order to get the Fourier representation of my output, that is y of t, denoted as y of f, that is the multiplication of all the filters. HT of f, HC of f, HR of f into X of f, correct? So that's what we have written here. You can see here, y of f is equal to input X of f, transmitting filter HT of f, the channel HC of f, and multiplied by the receiving function, that is HR of f, right? So in order to get this, what we can do here, we know what is the representation for X of f and y of f. Substitute, right? So from all the previous equation, left hand side I'll substitute. Left hand side means equation number 5. Substitute from there, I get a summation representation in this way. So summation minus infinity to infinity mu ak p of f e to the power minus j to pi f t. Direct substitution from the right hand side of equation number 5. Right? Similarly, x of f is written in another form of summation, right? So summation k minus infinity to infinity. See original signal, right? So ak is there. Ak g of f shifted function. So e to the power minus j to pi f k. Right. So again, mathematics says that if you have the same limits on both sides, you can cancel. So summations get cancelled. After you cancel the summation, if you get the same variables, you can cancel. So ak cancel. Same functions exist, cancel. So e to the powers are same on both sides, they also get cancelled. Whatever is remaining, we'll write then as equation number 6. Left hand side mu into pf. Right hand side gf ht of f hc into hr of f. Is it okay? Now what we do, equation 4 we try to refer, which says that y of t is equal to, it's a summation mu ak p of t minus t. So if I say that y of itb, let me put t as itb because you are trying to sample it out, right? So whenever you say I'm trying to sample it out, I'm going to put t is equal to it. This is the condition for sampling. Is it okay? Let's sample. So when you sample that, right, everywhere in the equation, you are supposed to replace the continuous time variable t, small letter t, by I into dv. You see, that's what is happening here, itb. That's what is happening here, itb. Okay, so itb we try to do. Okay, so that means I can take the tb common from the right hand side inside the bracket. It is I minus k into tb. Right. Now we already have assumed something. If at all the uh, inside the bracket I get a 0, the magnitude is 1, right? P of 0 is 1. So when the P of 0 becomes 1, whenever the I is equal to K, correct? So because of that, now I try to rewrite this. Y of ITB is equal to mu into AI, because I is equal to K. So AI P of 0 plus the remaining part of the summation all the way from minus infinity to plus infinity, but k cannot be equal to I. Which one? Which part we are assuming now? P of 0 is 1. I'll show you. You see here, this is the one. We already assumed that. Okay, we assume that P of 0 equal to 1. Whenever you assumed what the characteristic of P of t, right? This time, then itself we actually declare that it's a pulse, but at 0 its value is 1. Other than that, any value is fine. Right. So that's the pulse shaping function. This is assumed because most of the time, any pulse you take, at the center, its value will be retained as 1. Other than that, you can have various shapes. You can see one diagram here, which I have written. You can refer to that, right? So originally, this is 1, but other shapes of pulses do exist where the maximum value can be 1 at the center. Other values might change. Okay. Right. So because of that, we have written. Okay, so now you see y of itb is equal to this equation. So since p of 0 is 1, I can update in this way. Okay, y of itb, the sampled output will be mu into ai plus some other parts which is coming from the summation. So summation contains p of I minus k into t, right? And I is not equal to k, right? So it's different, right? Different p's will come into picture. In the sense, the past value of the pulse p, second past value, third past value, and so on. Because k varies all the way from minus infinity to plus infinity. Okay. Now let us assume that I'm trying to receive the ith symbol. Okay. So y of itb is the ith symbol. Okay, that means look at the equation on the right hand side, equal to, after equal to, I have mu into AI. So mu is a amplitude reduction factor, right? Some factor, but I have AI over there indicating that it is the amplitude of ith sample itself. So ith received sample should be ith transmitted sample. That's what is true here. Mu into that because it gets scaled down by a factor mu, right? So received sample is equal to first term, that is the sent symbol itself, amplitude of the sent symbol, but scaled down by a factor mu. That's fine for us. I'm receiving whatever I am sending. But there is a plus part. There is a plus all the way from minus infinity to infinity. Mu into ak. What is ak? K is not equal to I. So k is different than whatever is the I value. It means it is not the present sample. It is maybe other sample, all the other samples. So the overall idea is that my left hand side, which is the current received symbol, equal to, right, the actual sent symbol plus the effects of all the other symbols sent so far. So that means my current symbol is getting affected by all the other symbols. In other words, you call it as a ISI, right? So we write one sentence below this saying that the second term represents the unwanted contribution of all the other transmitted symbols or transmitted bits. That's equal to, that's because I is not equal to k, right? K equal to I means, okay, the current symbol you are receiving, same the current symbol itself was sent. But since it is not equal and k is all the way from minus infinity to plus infinity, it means it is the effect of all the other transmitted bits on the decision of the current bit, right? So you see, if the current bit amplitude is less and if you have other amplitudes larger, definitely the receiver is going to make an error. Correct? So that's why this unwanted component is what we refer as ISI in communication, inter-symbol interference. Okay, one question uh, can be expected saying that explain the whole concept of ISI. Right, starting from the initial thing, you can explain the whole concept here. Right, then the next concept under the ISI is about uh, it's about a condition, right? Nyquist has given a condition. It's called as a Nyquist criterion for zero ISI. If you don't want to have ISI, what is the condition that needs to be met by the binary baseband transmission system? It's a statement, right? The statement is below, right? The pulse shaping function P of t. It's all about the pulse shaping function, right? If you want to have a distortion less or the zero ISI transmission, right? What should be the pulse, right? So the pulse shaping function p of t with the Fourier representation p of f that satisfies this condition. Summation of the pulse shifted in the frequency domain from n varying from minus infinity to plus infinity equals to capital TB has the other kind. There are two things. You can use one of the given equation to prove the other. Okay, has p of I minus tb minus ktb is 1 for I equal to k, otherwise it is 0. This is the condition. Okay, all right. So we start the whole concept from sampling the pulse shape, pulse, right? So let us say we have a pulse shaping function denoted by p of t. Okay, that p of t, we try to sample it using what is called as a direct Coombe function. It's a sense, in the sense you have repeated the delta function at duration tb, right? All the way from minus infinity to plus infinity, right? So that is denoted by s delta of t, delta function repeated. Whatever is the gap between the delta function, you can assume. But since we want to maintain the sampling duration equal to the capital TB, here we assume that this is the gap between every delta value is equal to capital TB. Okay, so mathematics says that you get a sample if you multiply the original function p of t, multiply that with the delta function, a series of delta function, that is s delta of t, and the result is p delta of t. So here you see p delta of t is the sample result of sample. Okay, p of t is the pulse, original pulse. Okay, s delta of t is a series of delta function or Dirac-Coombe function. Okay, delta of t minus something, delta of t minus, right, 2 times that, delta of t minus 3 tb and so on. That's what is the s delta, right? So multiply to get the result of sampling. You get only sample values at every tb points, that is p delta of t, which is a sample of p of t. All right, let's proceed. Now take the Fourier representation on both sides. On the left hand side, I get p delta of f. Right hand side is a product, so product gets convoluted on the frequency domain. That's why we are using a property called convolution property of Fourier representation, which is written inside the rectangle, you can see here. Okay, all right. So since I have a product on the time domain, that's the second function, x of t into y of t. Frequency side, x of f convolution y of f. That's why it is capital P of f convoluted with the s delta of f on the frequency side. Equation number 1. Okay. Now let us try to look at more detail, right? That's what is the s delta of t. It's a Coombe function denoted by summation k minus infinity to plus infinity. Since delta function is getting shifted, it is delta of n minus kt. Put k equal to 1, n minus tb. K equal to 2, n minus 2 tb. Plus put k equal to minus 1, n plus tb. And so on. You can see delta function getting repeated everywhere. Series of delta. So take its Fourier representation. So very special feature of the uh, series of delta function is that you have a delta function, take its Fourier, that's also a delta. Only one function in the whole world which satisfies this. Fourier as well as the time domain signals are the same shape. Okay, so that is what we denote it as equation number 2. Only thing is that there is a scaling factor equal to fs. Whatever is the sampling rate, that gets multiplied. Okay, so s delta of f is equal to fs summation n minus infinity to infinity delta of f minus n into fs. Okay, where fs is called as a sampling frequency, that is also called as the rate of transmission, rb, bit rate or symbol rate, that is calculated as 1 divided by the time duration, that is tb. So by from our basics, we know that 1 by time duration is a frequency, right? So that's what is the equation number 3. You take 1 by time, you get a frequency. I hope it is fine. Okay, right, let's proceed further. So now my intention is that I want to put equation 2 and the equation 3 in the equation number 1, which is a convolution. So write that. So P delta of f is equal to, first function is P of f convolution. The second function I'm writing from equation number 2, which you can see here. So when you substitute that, you get this as the right answer. RB, because Fs and RB are same from equation 3. RB into summation n is minus infinity to infinity delta function, right? Repeat it. So again, going to the basics of signals and systems, where we see if you convolve any signal with a shifted delta function, the function gets shifted to the location of the delta function. You see, delta is located where? T minus T naught. In the sense, it is located at T naught. So x of t, if you convolve, the x of t goes to the location T naught. So denoted as x of t minus T naught. So you see in the above function, I'm actually in the above equation, I'm convolving P of f with the delta of f minus nRB. Those are the two functions which are getting convolved. Others are constants, right? RB is a constant, it remains out. Summation is just an operator. You don't have to deal with that right now, right? So what you see, P of f goes inside the summation and gets, right, written as equation number 4 shows P of f minus nRB, right? Because delta function was located at nRB, right? Your P of f gets shifted to that position, P of f minus nRB. So outside I still have RB and the summation as it is. Is it okay? That's what is equation number 4 is all about. Now we hold on to this for the time being. We will go back to the P delta of t and its Fourier representation. So P delta of t, the sampled version of the pulse function, right, has a Fourier representation denoted by P delta of f. Okay, so equal to minus infinity to infinity P delta of t e to the power minus j2 pi f t dt, the basic equation of the Fourier transform. Whichever function you want to write, integrate that after taking a product with, right, e to the power minus j2 by f. Right. So p delta of t is my function. I multiply that with e to the power minus j2 pi f t and then integrated all the way from minus infinity to plus infinity. That's what is the equation, right? That is for obtaining the Fourier representation. Okay, that's equation 5. But I also know that P delta of t is P of t into S delta of t. But S delta of t is M is minus infinity to infinity. Delta of t minus MT. Correct? So I can try to write that the whenever this P of t, I want to put it inside the summation, I have to bring the MTB into picture because it's going to, whatever is the value of the pulse at the location MTB is what is going to be used to calculate the answer. So that gives you the equation number 6. Okay, P of t goes inside the summation, that's all. Okay, now you see we have the P delta of t denoted by equation number 6. I want to put that in equation number 5 in place of P delta of t. So you just check, right, one by one term. So on the left hand side, I still have P delta of f equal to, there is a integration. Then I have a P delta of t which is replaced by the summation in equation number 7. Summation m minus infinity P of mtb delta of t minus mtb. That's a P delta of t. Multiply this with e to the power minus j2 pi f t dt. All right, very straightforward. Now we'll try to put or replace the I minus k by m, that is it, right? That means I is equal to k means m equal to 0 and I not equal to k means m is not equal to 0, right? That's what I'm that's what is my conclusion from this. Right, now let's go back, right, and write the P as P of I minus KTB. Some MTB we already have written here, right? So you can see that there is a MTB here. That M is nothing but I minus K. Just now we assume, right? So that I'll write here in the next line. So P of I minus K TB is nothing but the P of MTB. That is going to be 1 when M equal to 0, right? P of MTB, if M is 0, it becomes the center. Already we know that it is 1. And it's going to be 0 for M not equal to 0, right? So let's use this logic in equation number 7. So I don't have to write a summation because it is going to exist only at P of 0, right? Into the delta. Delta of MTB becomes just T, delta T. So you can see here, I'm writing just delta T. I'll show both the equations so that you can compare. Okay. So P of MTB becomes P of 0. There is no summation going to come now. Okay. Because all the other values, it's going to be 0, right? So M is not equal to 0. It is, we already have written equation 8 says that it is 0. So the pulse is not going to come into picture at that location. Is it okay? Not equal to 0. It's 0. Okay. It's 1. So the pulse is going to exist only when M equal to 0. So in equation number 7, you see there is a summation. The summation is M is minus infinity to plus infinity. So that makes no sense because only at M equal to 0, it is 1. All the other values, it is 0. So don't write the summation, remove the summation and put only that value which exists. Which it exists is P of 0. When M is equal to 0, delta of T minus MTB in the equation number 7 becomes delta of T. Right? And you multiply by e to the power minus j 2 pi ft dt. This is already present in equation number 7. Right? Okay. Now you see, I have a integration to solve. Inside the integration, I have a product. Okay. But whenever you have a delta function inside the product, inside the summation, inside the integration, 99% of the time, you don't have to integrate at all. Okay. Because of this reason. Why? I'll tell you now. So, okay, let's consider a diagram wherein in this equation P of P delta of F, there is a value P of 0. Okay, some value P of 0, which is equal to 1 anyway. I know that. I'm going to replace that P of 0 by 1. So neglect P of 0. There is a product. What is a product? The product is delta of T into e to the power minus j 2 pi ft. But for the time being, I don't want to consider the exponential, complex exponential. I will call it as a sum f of t. Okay, now you see there is a product, a delta function into a f of t. So right hand side, you can see a diagram I wrote earlier. So this black colored wave or the function is f of t. I marked on the top, right? The black color. Again, on the horizontal time axis, I marked at 0, I have a delta function. So, right, again, I understand that this whole integration is of no meaning to me just because, right, the function delta function does not exist anywhere other than t equal to 0. So there is no meaning in integrating t equal to minus infinity to plus infinity. Same reason why I removed the summation in the previous case. Summation m is equal to minus infinity to plus infinity, I simply removed because it was existing only at one point. Right? So same reason here. You see the delta functions exist at only one point, and at that point, whatever is the f value, take a product, correct? Because delta of t is 1. Right, at that point in the sense at t equal to 0, how do you find out what is the value of the function f? It is f of 0. Right? So it's actually f of 0 into 1. No need to integrate. So the answer, you can see, I have written a rule here. This is the fundamental rule we studied in signal sound system. If you look at an integration minus infinity to plus infinity, delta of t into any function f of t dt, that is equal to f of 0. Right, let's go back. So the updated equation 7 we can see here. In that, I need to put t equal to 0. That is, in the function e to the power minus j 2 pi of t, put 0 over there for t. Other values remain as it is. So p of 0 into e to the power 0 into the delta function, which is 1. So this becomes p of 0, that is equal to 1. Right? On the left hand side, what I have p delta of f. So p delta of f is equal to 1. This is what I get. That is equation number 9. Right. Let's go back and check the equation number 4, which we held previously. We told that, okay, just hold on to this. We'll come back to this later, right? So now I go back to that equation number 4, which is once again written here. On the left hand side, I have p delta of f. Right hand side, you have, right, rb into summation of the capital P of f minus nr, right? But just now we proved from equation 9 that p delta of f is equal to 1. So left hand side replace 1. So 1 is equal to rb into the summation. But you see, the statement says that you have to have the right summation on one side and rb going to other side. So rb when moves to other side, it becomes tb. That's all. Okay, so RB was written in this fashion, right? RB equal to 1 by TB. The TB goes to other side and you get this. So this is the proof, right? So same equation, whatever we have written inside this red colored block is the proof, is the final answer. That's what they had asked us to prove. Okay. Do you have any doubt with the whatever we discussed in this? Okay. All right, let's move further. So after the ISI and the what you call as the condition for zero ISI, we move on to the next topic, that is actually about measuring the distortion present in the received signal. Okay, it's called as the I diagram. Right? So it's a plot we can see on the oscilloscope to study, or you can even measure the amount of ISI. And also, not only just ISI, you can also measure various signal degradations that are possible. Okay, amplitude, or how much error present whenever the signal crosses 0, etc. Many things we can measure. What are the measurements you can do? We'll see later. So first we'll look at an example how this is going to look like. If you use a square wave like this, right, I'll be seeing this on the right hand side. Whatever you see here on the right hand side will be our the I diagram. But we cannot call it as an I because there is no I over here. Normally what you use a sine wave or a cos wave, or in general any sinusoid. Okay, whenever you use a sinusoid, you will be able to see a I like structure that is seen on the right hand side. Okay, so the height is called as opening, and right horizontal distance between the least points, that is zeros, two zeros present over here, is called the width of the eye. So height of opening of eye represent and the width of the eye, these are the two parameters which we can see on this. So there is a specific way to get the what you call eye diagram on the screen of the oscilloscope. Normally by just clicking the buttons you get this. Okay, so digital oscilloscopes are very easy to handle. There will be so many buttons on the right hand side of the screen that will directly plot whatever you want. But olden days we didn't have so much sophisticated devices, right, where you used to adjust many things to get the eye diagram. Eye diagram was possible, but not as easy as a digital oscilloscope. Okay, anyway, right. So now we'll see how do you interpret. Okay, this is how it looks like, we understood, but we already mentioned that by looking at the eye diagram, you should be able to measure something, or you should be able to understand, is there any distortion? What are the various distortion you can measure? Right? Is what, right? We need to look. So this is called as an interpretation, right? So this diagram shows on the outermost side, whatever you have is the maximum size of the eye, and maybe let us assume that the innermost shape what you see here is the minimum size, okay, of the eye. Okay, if at all your eye diagram vertically varies between these 2 points, then there is a distortion at the sampling period, right? Because this is my total time period. Okay. When I say I have a total time period like this, right, the horizontal time period which you can see at the bottom, right, normally we sample at the midpoint. always you try to sample at the midpoint. So during the sampling period, you have a distortion. That is a meaning of having variation in your eye diagram at the center, on the top. Okay, right. So the highest value peak comes means you can actually sample at that instant. That's what is the time instant. So horizontal axis is still time. On the time axis, I'm getting a graph. Okay, then right, we measure another aspect here that is called as a noise margin. Right, you might have not have used this term so far, but just remember there is a term. It's actually a measurement of how much noise is present. Right, it's another version. Right, we'll come to that maybe later, but you see that this measurement from the horizontal central axis, central line to the this line is called as a noise margin. How much it varies. Okay, again, the width over here represents the distortion at zero crossing, because this is the red line you see here is the zero line. So whenever it crosses, there may be a distortion this much. That's the width. Okay, and also we have another error that can be measured, which is called as a timing error. That is, what is the slope of your straight line. Again, it's not straight line always. If it is not a straight line, you would consider the tangent, because slope of any curve is a tangent, right? At that point. So you can actually use that also. That's called as a sensitivity error over there. So these are the various parameters we can measure from the eye diagram. So whatever terms you have never heard so far, don't worry, it will come later, right? But just remember that, oh, there are terms like this, and these are the terms which you can measure from the eye diagram. That's what is important. Okay, explain eye diagram question comes, give an example such as like this, write it in your own sentence. Then you say, okay, these are the various parameters we can measure. That's all. Okay. All right, let's move further. The next thing is called as a correlative coding, right? So this is a technique which gives us an idea that, no, ideally speaking, we cannot have uh, any amount of what you call ISI. ISI is not acceptable. Okay. But if you have two symbols continuously, like 1 1 or 0 0, right? Definitely the one which is the first one will enter into the second one, or the second one will enter into the first one after a certain distance, like whatever I have shown here on the right hand side, right? So but now you see the sampling or the decision making will not affect now, will not get affected, because at the center of 0 to TB you still get a high value. At the center of TB to 2 TB I still get a high value. So sampling will not affect, will not get affected, right? So that's the point, right? So in the sense, uh, so this concept leads to an idea that, okay, if at all I have continuously, right, same symbols repeating or same bits repeating in my message signal, right, can I allow the ISI to happen, or is it possible to introduce the controlled way? All right, ISI can be introduced in a controlled way, so that, right, it will not affect the uh, decision made on the receiver side. That's what is the concept, right? For that you will do slight modification in your code before you send, right? And that concept is what is considered as the correlative coding. So you try to look at the correlation between the present and the next symbol, and if they are same means you, right, you can introduce the whatever called as ISI. You can sum them up and you can send it. So that's what is the idea. So we look at the fundamentals. So let us say we have a pulse P of n dB. It is 1 for n is equal to 0 and 1. Means I am considering two consecutive pulses. Okay. Anyway, NRZ format works very fine for us. So we assumed NRZ format. Okay. Now let us say this means P of NTB actually refers to two successive pulses, P of T minus TB. Is it okay? All right. Now let us say whenever they both of them are positive, right? At the center, whenever you try to sample it out, you will be having 2 as the answer, because 1 plus 1, right? At the same time, if at all they are negative, like you are trying to send two zeros, okay? Or it's, let's say it is -1, -1. Two zeros are being sent, but their coding will be -1, -1, right? Okay, that means, right, the sum will be at the point of sampling, you will get a -2. Okay, proceed further. Take the other possibility. They are opposite polarities. One is +1, second one is -1, or the vice versa. First one is -1, second one is +1. Okay, what happens to the sum now? So that means sum will be equal to 0, right? So the fundamental concept is that, right, what are the various possibilities you are going to get when both the signals are same, in a sense, same in the sense positive, same but negative. The third case is opposite, right? So we understood that. So this is what we try. Now we try to make a rule for, or a logic for making the correct decision on the receiver side, provided ISI is allowed. Okay, so that is 3 points. Whatever we wrote earlier, we are writing it in a different way. So it's a reverse of whatever is written. I say I got a positive value, means the present and the past bits are ones, right? Because plus A, you had plus A, it becomes +2A. So whenever you have a positive answer, neglect the A part, you have a positive answer, just take a sign. Positive means it is 1. Okay. The second point we assumed earlier, we understood earlier, says that we received a value and that is negative. Okay. Whenever that is negative, I should understand that the present and the past bits are zeros. Right. So because both of them were negative, sum is again negative. Right. The third case is that if at all you have a sample value which is 0, right? So present and the past bits are complements. One means other one is 0. So right now I have 0 means other one is 1. Right. Now, by if you use this particular way of coding used for, right, the pulse shaping techniques, right, as a technique, it's a coding technique. It's called as a correlative coding, right? So the idea behind the correlative coding is that you try to introduce the ISI in a very controlled fashion, right? So in a sense, it's not at random. It's not going to be uh, a large amount of ISI, little bit of ISI. Okay, so because two things are added together, the neighboring samples are added together to get a new value. So whenever one affects the other one, it itself is a ISI. But you don't do this for every values, you do this only for consecutive values. Okay, so original concept of ISI was you are considering the current symbol and all the other possible symbols, right? Now you are not doing that. You are considering it's now we are calling it as a controlled ISI only because the ISI between the present and the next symbol is only considered present and the past symbol, maybe. Okay, because third one, if the sample value is 0, then the present and the present bit is a complement of previous bit, right? Okay, let's go back. You see here, uh, this is the point. If P of t, present one, P of t minus tb, the past one, are opposite, okay? If they are opposite, what happens? Sum is 0, right? Because the first one will be +1, second one will be -1, opposite polarity. What happens when you add? You get 0, right? Now I am writing the reverse of this. I am writing the same thing in a reverse way, right? If at all I receive 0, that means the present and the past symbols will be complement of each other or opposites of each other. That's what is my actual logic when I write below. Okay? Huh. One before. It's like consecutive. Again, the whole concept is the consecutive bits only. Correct? So if the sample value, current value 0, that means the sum of the present and the past value is 0. Correct? What do you mean by that? Whatever is the present value, past one is opposite of that. Then only you get 0, right? Plus 1, then only you get 0. Otherwise, uh, yeah. So present value is 1. Past value should be the complement, which is minus 1. That's all. Okay. You are coming to a conclusion that, okay, now I received 1. Past one should be minus 1 because my sum is 0. Otherwise, present value is minus 1, which means the past value has to be, right? Present value minus 1, past value has to be plus 1, which indicates that, okay, current, the sum which I got 0 because of this. That's all. Now you see, I'm trying to decide what is my present and past value by looking at the sum. That's all. So in this particular case, there is a special case. There are many correlative coding techniques. One which we are going to see is the duo-binary signaling, in which you are trying to send the sum. Either you send the sum like zeros or positive values or the negative values, using which you will be able to decide what has been received on the other side, on the receiver side. You will be able to decide what has been sent. Okay, so that part is going to come in the next class.